Hello, in this video we're going to discuss simplifying radicals in rational exponents. Hopefully this is something that is you may have learned in a different class, but we're just going to start with the very basic issues. When you have a square root, suppose you have the square root of 50. If you want to simplify that in the most basic way possible, you might recognize that 50 is the same as 25 times 2. 25 is a perfect square. If you have two terms that are under the radical that are multiplied, you're always welcome to break them up into individual radicals that are multiplied together. So this is going to be the square root of 25 times the square root of 2, or just 5 square roots of 2. Very simple. If you had something like this, the cube root of 40, 40 is the same as 8 times 5. So this would be the cube root of 8 times the cube root of 5. And the cube root of 8 is a question of what number multiplies with itself 3 times to make 8. 2 times 2 times 2 does make 8. So the cube root of 8 is 2. This is 2 times the cube root of 5. If you are adding or subtracting radicals, the key is what's inside the radical and the root itself have to match. So for example, if you have the square root of 200 minus 3 roots of 2, obviously 200 and 2 don't match currently. So you would have to say, 200 is 100 times 2. So I'm going to write this as 100, root 100 times root 2 minus 3 root 2. The square root of 100 is 10, root 2. 10 root 2 minus 3 root 2 is going to be, excuse me, 7 root 2. So once you have the same root and the same number under the root, you're just dealing with like 10x minus 3x is 7x. 10 roots of 2 minus 3 roots of 2 is 7 roots of 2. When you have something with a root and then the number under the root, you can write that as a fractional exponent. The square root of 2 is the same as 2 to the 1/2. The square root of 5 is 5 to the 1/2. When you have a fractional exponent, the bottom number is the root, and the top number is the power. If you had something like the cube root of 25, that doesn't have a nice root, but you could write it like this: the cube root of 5 squared. That's the power, that's the root. This is the same as 5 to the 2/3 power. If I asked you for 8 to the 5/3 power, this is the root, this is the exponent. Now you've got two options. You could take 8 to the 5th power, a very, very large number, and then take the cube root of that. No thank you. Or you can take the cube root of 8 first and then take that to the 5th power. So you can write this as the cube root of 8 to the 5th. That's the power, 5. This is the root, it's 3. The cube root of 8 we saw earlier is 2. 2 times 2 times 2 makes 8. So this is 2 to the 5th. And 2 times 2 is 4, 8, 16, 32. So just kind of an introduction to simplifying exponents. Just like any exponents at all, if you have 5 to the 1/3 to the 6th power with parentheses, the power on the outside multiplies times the power on the inside. That would be 6 times the 3rd, or 2. So that would be 25. And then finally, if you had 5 to the 1/3 times 5 to the 2/3. If you have the same base, you add the exponents together. So 1/3 plus 2/3 would be 5 to the 1, which is 5. Okay. Let's get a little bit more creative. Let's do something. That's the 5th root of x to the 10th, y to the 5th. This isn't too much different, but if you want to simplify this, you take the root, and the root is going to apply to everything inside the root as long as everything inside the root is either multiplied or divided with itself. So this is going to be the 5th root of x to the 10 over the 5th root of y to the 5. This is going to be the power is 10, the root is 5, x to the 10 over 5. Here the power is 5, the root is 5, y to the 5 over 5, which is x squared over y to the first. Okay. If you have something like this, x times the cube root of y to the 6 plus y squared times the cube root of x cubed, you can only add these together if you have the same root and the same thing under the root. So this obviously doesn't, and so we need to do some simplification first to see if we can add these together as like terms. This is a power of 6, a root of 3, so I'm going to write this as x times y to the 6 over 3. And then we're going to have this as a power of 3, a root of 3, x to the 3 over 3. So 6 over 3 is 2xy squared. And this is x to the 1, and that's y squared. So we actually have xy squared twice. So that makes 2xy squared. So once you have, you can only add apples and apples, oranges and oranges. You have to add or subtract like terms. So if these had not been the same thing, then we could not have added them together. Likewise, if you're trying to add this together, just right off the bat, those don't appear to be able. It doesn't look like you can add them together because 176 and 11 are not the same number. But take a closer look. 11 is prime, so I can't really do anything. I can't break down 11 at all. But 176 is not prime. Think about 11. 11 goes into 17 one time, into 66 6 times. 11 times 16 is 176. Let's write this again as the 4th root of 16 times the 4th root of 11. And then we have that right there. The 4th root of 16 is actually 2. 2 times 2 times 2 times 2, all 4. 2 times itself 4 times would be 16. So we have this, and then 5 times the 4th root of 11. This is 4 4th roots of 11, 5 4th roots of 11. That adds up to 9 4th roots of 11. So sometimes it helps just to spend a moment and see if you can make what's underneath the radical, make those match. Okay. Still kind of on that theme, let's try this. 125 to the 2/9, 125 to the 1/9 over 5 to the 1/4. So in this case, the 125s do match. I can do something with those. The 5 doesn't match. They're not the same base. So we need to deal with that. For 125 to the 2/9 times 129 to the 1/9, I can rewrite that as 125 to the 3/9 by adding them together. And then 3/9 actually happens to be 129 to the 1/3. So now we're stuck. We've got two different bases, and so we need to find a way to make them have the same base. And I want to just point out that 125 is also the same as 5 cubed. 5 times 5 is 25. 25 times 5 is 125. So I'm going to write this as 5 cubed to the 1/3. And we've got 5 to the 1/4. So 5 cubed is 125. And like I said earlier, if you have parentheses, an outside exponent times an inside exponent, 1/3 times 3 is 5 to the 1st. And then 5 to the 1/4. And so now we do have the same base. We're fortunate. We have 5 to the 1 over 5 to the 1/4. Just like you add exponents together when you multiply, when you divide, you subtract them. So now you're going to do 1 minus 1/4 is 5 to the 3/4. And once again, this is the root. This is the exponent. So you could leave it as 5 to the 3/4. But if you're doing a multiple choice question, they might write it as a root. So this would be the 4th root of 5 cubed, which is the 4th root of 125. Be prepared to change the format of your answer to match the answer choices that are provided. Okay. One more kind of like that. So last time, in this previous problem, the 125 and the 5 are all related. The exponents were completely different. In this case, the 6 and the 4 and the 3 don't really seem that related. However, the exponents are all exactly the same. So if the exponents are all the same, one option you have is to take the 2/3 out in a parenthesis and rewrite this as 6 times 4 over 3. So that's a really simple way. If you notice that, if the bases match, woohoo, that's awesome. That really speeds things along. But if the exponents all match, you also have a shortcut available to you. 6 times 4 is 24, and divide that by 3, and you get 8 to the 2/3. This is the root. This is the power. This is really the cube root of 8 squared. The cube root of 8 from the 3. The square from the 2. And the cube root of 8 we've seen a couple times as 2. And then 2 squared is 4. Okay. Let's play with more x's, y's, and z's and fewer numbers, but using the same rules. Just something like this. We're going to simplify. If you write these as, I guess you got a couple options. You could write this as an exponent 3/4, 5/4. If you take 3/4 and 5/4, you get 8/4. This is one option here. You could write this as x to the 3/4 times x to the 5/4 to the negative 2 power. That is x to the 8/4 to the negative 2 power. X squared to the negative 2 makes x to the negative 4, which is 1 over x to the 4th. So that's one option available to you. Another option is you could write this as, because these are both the same 4th root, you could just do x to the 3 times x to the 5 and make this the 4th root of x to the 8th to the negative 2. And what multiplies with itself 4 times to be x to the 8th? How about x squared times x squared times x squared times x squared? So this is x squared to the negative 2, x to the negative 4, again, 1 over x to the 4. So that's there's two ways to kind of think about that, just to kind of get going there. Let's keep rolling. Sometimes you may have something that looks like this, and you're just asked to simplify it. X to the 5th, y to the 8th, z to the 10th. So here, I'm feeling kind of like I might strike out because there don't appear to be any real obvious like perfect fourth powers. So here's what you're going to do. Now with the 10, yeah, there's really no place to go with the 10. A nice, one of the smallest fourth powers is 16, 2 to the 4th is 16. So what I'm going to do is I'm going to rewrite all this stuff under the fourth root, and I'm going to break it up into things that could be a nice fourth power and things that might not be. So with x to the 5th, I'm going to write that as x to the 4th times x to the 1. Y to the 8th does have a nice fourth root, so I'll just leave that be. For z to the 10th, I'm going to write that as z to the 8th times z to the 2. So what I've done here is I've said this and this and this. All those things can come out. If I take the fourth root of x to the 4, that's just going to be x to the 1. The fourth root of y to the 8th, 8 over 4 is y to the 2. For z to the 8th, 8 over 4 is 2, so that's z to the 2. And then remaining, I have all the leftover junk, the 10, the x, the z squared. So that is as simplified as I can make that. All I did, like I said, I broke up the x and the y and the z into things that kind of did have a nice even fourth power that I could take out this and this and this. Took out what I could, and then the leftover was just kind of remaining back there. Okay. Another example, 8x y to the 7th, fourth root of that, times fourth root of 6, x to the 6. So here I've got some options again. One option is to take the fourth root of, break this up into y to the 4th times y cubed. You could do that. You could break this up into x to the 4th times x to the 2nd. I think here, because the 8 and the 6 don't have nice fourth roots, I'm going to be better off multiplying this all together first. And the reason is 6 times 8 is 48. X to the 1st times x to the 6th will just make that x to the 7th and y to the 7th. And it's not really going to make a big difference for the x's and y's. But notice 48 is the same as 16 times 3. And so if you take these two numbers that don't, both of them individually don't have nice fourth roots, if you multiply them together to something bigger, you now have a chance for a nice fourth root. So I'm going to go ahead and just write this as the fourth root of 16 times 3 times x to the 4th times x cubed times y to the 4th times y cubed. And this and this and this all have nice fourth roots that can come out. The fourth root of 16 is 2. The fourth root of x to the 4th is x. Y to the 4th is y. Remaining is a 3, an x cubed, and a y cubed. So that's that. Let's see here. Take this sheet off. Oops. Okay. And maybe just a couple more. do square root of 7 x to the 8th. Okay, oh, sorry, there we go. So this is a subtraction problem. In order to make this subtraction problem work, in order to perform subtraction or addition, we have to have the same thing under the radical. So in this particular case, I have 7x to the 8th. Here I have 7x to the 12th. They don't match. So what I'm going to do is I'm going to take the x to the 12th. I'm going to break that up into 7x to the 8th times 7x to the 4th. Now, if I just took the square root of x to the 12th, that would be x to the 6th. You know, that's fine to do, but I want this to match. I want these x to the 8ths to match for the sake of doing the subtraction, and then we'll kind of see where we go from there. Oh, I didn't mean to have a 7 there, sorry. 7x to the 8th times x to the 4th. And so x to the 4th can come out on its own. The square root of x to the 4th is x squared. So I end up with something kind of like that. We've got 7x to the 8th now, 7x to the 8th. This x to the 4th, we took the square root of it, and we got x squared. And now, because these two match, all I do is I subtract the coefficients. So I have 13 minus 3x squared times 7x to the 8th. And we're actually not quite done yet, because I'm noticing x to the 8th itself could be broken down. So we have 13 minus 3x squared times the square root of 7 times the square root of x to the 8th. And x to the 8th, the square root of that is x to the 4th. So this is 13 minus 3x squared times x to the 4th times the square root of 7. And the last thing I want to do is multiply this x to the 4th through. So we'll have, and I can just multiply the x to the 7th through too. 13 x to the 4th root 7 minus 3 x to the 6th root 7. And like I said before, you know, you never know how the answer choices are going to be presented. So you could have 3x to the 6th times root 7. Either one of these is a viable answer where I just factor out the root 7 there. So I think this will pretty much wrap you up. Like I said, we've been just introducing the concept of rational exponents, where if you have a fraction in the exponent, the top number is the power, the bottom number is the root, and we've just been adding and subtracting, simplifying roots, and that's it.